It says that on any disk in the complex plane, the hyperbolic metric on the disk is comparable to a very simple and easily understood metric called the 1/d metric. And comparable means they have a bounded ratio. In fact, what we will see is that this can be made more precise. 1/2 rho 1/d is less than or equal to rho u is less than or equal to 2 rho 1/d. Okay, so what does this statement mean? When you have a domain in the plane and it's isomorphic to a disk, we have a point z, we can measure the distance from z to the boundary. That is, look at the largest inscribed disk. And the 1/d metric at that point z is just equal to 1/d, 1 over the distance from z to the boundary of the disk. And the hyperbolic metric, on the other hand, is defined in a complicated way. We find the Riemann mapping isomorphically from the disk to u, and then we take the hyperbolic metric here and we transport it to u. So that's defined by some complicated and sometimes inaccessible analytic procedure when the domain u is very complex or ragged. This metric we can always visualize, very simple. It says that if we draw a small stick figure and its height is comparable to the distance to the boundary, then in this metric its diameter is about 1, but then in the hyperbolic metric its diameter is about 1. So we have a good idea of the sizes of things within a bounded error. Okay, so that's the idea of the 1/d metric. And let's look at some examples. Suppose we're in the case where u is equal to the upper half plane. What is the hyperbolic metric on the upper half plane? It's dz over the imaginary part of z. Okay, now what's the 1/d metric? What's the distance from the point z to the boundary of the upper half plane? Who can tell me?
Imaginary part of z again.
It's the imaginary part of z again. So this is equal to the 1/d metric. That's a good hint that they might be closely related. Now on the unit disk, things are a little bit different. When z is close to the boundary of the disk, the distance from the boundary is like 1 minus the absolute value of z. And the hyperbolic metric on the unit disk is 2 dz over 1 minus the absolute value of z squared. But if we factor this, we'll get 2 dz over 1 minus the absolute value of z times 1 plus the absolute value of z. And you can see that this factor here is just the distance to the boundary, and this factor tends to 2 as you tend to the boundary. So as you get closer and closer to the boundary, this looks more and more like the hyperbolic metric, like the 1/d metric. In fact, the 2 here cancels with the 2 here, and you get something that's asymptotic to the 1/d metric. When we looked at the strip S between 0 and pi I, we saw that the hyperbolic metric here was given by dz over the sine of y. And the sine of y, when y is small, looks a lot like just y itself. And y itself is in fact the distance from z to the boundary of S, at least when z is close to the lower boundary. When z is close to the upper boundary, it's more like pi minus y. But the sine of y is like pi minus y when y is close to pi. So indeed, in this example, it's also like 1/d. So that turns out to be a general principle. The hyperbolic metric on a simply connected region blows up like 1 over the distance from the boundary. Now, I do want to remark that this is false if we don't ask that u is a disk. As we saw already on the punctured disk, in the 1/d metric, we get the metric dz over z. and at least near the origin. That's what rho 1 over d. But to get the hyperbolic metric, we have to add in an additional factor of log 1 over the absolute value of z, which is unbounded. So these metrics are not comparable close to the origin. So it's really a special feature of simply connected domains. Okay, so that's one of the reasons I like to develop the results we're about to talk about, because they give you a good intuitive feeling for the hyperbolic metric. But the other thing I want to emphasize is that when one considers the space of all Riemann mappings, as long as you normalize the mappings a little bit, you're working in a compact space. And as I mentioned last time, that means anything we can think of that might be bounded is bounded, as provided it's a continuous function on the space. So there's two traditional ways to normalize these functions, as I've mentioned last time. The first, we normalize so they're maps from the disk in the plane, and they have power series expansions in the usual sense. And the second is they map the outside of the disk to the outside of a compact set, and then they have a Laurent series expansion. And so let me catalog some assertions about these spaces, and then we'll describe the proofs. And in the course of the proofs, we'll ultimately see a proof of this theorem. But I think this is the real takeaway, is that these spaces are compact. The rest is just finding sharp constants or attractive statements about particular features of these spaces. So one way to establish compactness is by what's called the area theorem. And this applies into the class sigma. So remember, in sigma, we're mapping the outside of the unit disk to the outside of some compact set. And we're going to revisit this situation over and over again. So we have an analytic map that sends infinity to infinity, and the target of the map, u, we have the Riemann mapping from the outside of the disk, 1 over delta to u. The target of the mapping is the outside of some compact set k of f. So this k of f plays a prominent role in the discussion of these maps, and it's bounded. So we could ask what its area is. And it turns out there's an exact formula. The area of the complement of the image of f is exactly pi times 1 minus the sum of n bn squared. The bn are these coefficients. Let's look at an example. The simplest example is where all this power series is 0, then the map is just the identity. What's k of f? It's the unit disk. The identity map omits the unit disk. Its area is pi, and that's what you get when this stuff here is not visible at all. Another important example is the map z plus 1 over z. If I apply the map z plus 1 over z to the outside of the unit disk, what's left over? What's the image of the circle?
Like the entire complex plane.
Well, the
Except for an
circle
interval.
can't map onto the whole
The
complex.
line thing from, it's the line from -2 to 2.
Yeah, exactly. Thank you. So it's the circle. It's this part here. The image, as Alex says, is dense in the complex plane, but it's not everything. The outside of the unit disk goes to the outside of this interval from -2 to 2. So that's our k of f. And this guy has area 0. Well, let's check that here. In that case, b1 is equal to 1, and we get 1 minus 1 times pi, which is indeed 0. This extreme mapping, where the image has no area at all, occurs again and again in conformal mapping, and in many different guises, as we will soon see. Now, one consequence of this is that the sum of n bn squared is less than or equal to 1. And this implies that bn itself is less than or equal to 1 over the square root of n. But you see, this already implies that sigma is compact. Because if we have a sequence of functions here, all of these coefficients in the power series are bounded. And the power series, by virtue of these bounds, converges uniformly on the disk where z is bigger than a given constant r. It has radius of convergence 1 in a uniform sense. So any sequence here has a subsequence where the bn's converge because they're bounded, and then that sequence converges uniformly on compact sets. So this is enough to imply already that sigma is compact. And of course, it gives individual bounds on all of the bn's. In particular, b1 is bounded by 1, and we saw that the extremal map is this one here that squishes all the area away. Now, for the class S, there's a bound like this, an is less than or equal to n. This is called the Bieberbach conjecture. And I'm not going to prove that, but I will prove the importance first case, which is that A2 is less than or equal to 2. But more to the point, the question is, can equality hold here? Can an actually be equal to n? And in fact, there's an important function in S, which is the function f of z is the sum from 1 to infinity of n, z to the n. And this function is easy to write down explicitly because it's because we know that 1 over 1 minus z is 1 plus z squared, etc. Most important power series in mathematics. And now if we differentiate both sides, we get 1 over 1 minus z squared is equal to 1 plus 2z plus 3z squared and so on, which is almost this function, but the exponents are off by 1. So this function is just z over 1 minus z squared. And it turns out that this function, which realizes the maximum value for every an, has a very simple image. This maps the unit disk to the complex plane slit from minus infinity to minus 1/4. So let's just see if that makes sense. When we plug in, as z goes to 1, the denominator goes to 0, so this goes to infinity. But as z goes to minus 1, the denominator goes to 2 squared, which is 4. The numerator goes to minus 1, so it converges to 1/4. Okay, so the image of this guy is the complex plane slit from minus infinity to minus 1/4. And remember, these mappings are normalized so that zero goes to 0. So the complement of is getting pretty close to 0, but it's still distance 1/4 away. Now, what I want you to notice is that up to Mobius transformations, this Riemann map is the same as this Riemann map. Any two arcs of circles or intervals on the real axis are equivalent up to Mobius transformations. So these are really the same map appearing in two different places. Now, in fact, one can say more. There is a sense in which this map is extremal that one can prove. It's not as hard as the Bieberbach conjecture. And that sense is that the distance from 0 to u, which is f of the disk, always lies in the interval from 1/4 to 1 for f and s. So you see here, the distance from the boundary of u is this interval, and the distance from 0 to the boundary is exactly 1/4. So the lower bound here is achieved, and it doesn't get closer than that. So another way to say the lower bound is that f of the disk contains the ball around the origin of radius 1/4. And this is called the Kuba 1/4 theorem. Now, in fact, knowing the distance from 0 to the boundary, this should have been the distance from 0 to the boundary of U, which is the boundary of f of the disk. Knowing the distance from the 0 to the boundary tells us what the 1 over d metric is. So what can we say about the 1 over d metric here? Its value at 0 is between 1/4 and 1. That's a corollary of this statement that I've just written down. And what about the hyperbolic metric? Well, the hyperbolic metric on the disk satisfies its value at the origin is equal to 2. And our Riemann mapping is normalized, so its derivative at the origin is 1. So the hyperbolic metric on U is also 2 at the origin. So we see the hyperbolic metric at the origin is 2, and the 1 over d metric lies between 1 and 4. It's the reciprocal of these numbers. Sorry, I should have put 4 here because the distance is 1/4, the 1 over d metric is 4. If the distance is 1, the 1 over d metric is 1. In any case, you see that this number and this number differ at most by a factor of 2. So that implies this theorem here. Okay, so the desired theorem is a consequence of what's called the 1/4 theorem. Okay. So I wanted to get some of these results on the board so that I can erase them and then explain at least some of the ideas in the proof. And what really gets everything going is this guy, the area theorem. This is a beautiful idea that we should have an exact relationship between the coefficients of a Riemann mapping and some geometric property of its image. So let me start this discussion by giving the proof of the area theorem. Are there any questions before we plunge into that?
Professor?
Yes.
So item 3 on the list, is this still a conjecture right now?
Oh, no, sorry. I did mention this last time. So this is called the Bieberbach conjecture. It was proved by de Brange in the mid-1980s. So this is not a conjecture, it's true. And the original proof was very difficult. It was about 300 pages long. There's now very economical proofs available. I know Yum-Tong Hsu, professor here at Harvard, sometimes presents these in his graduate course and even undergraduate classes. But it's rather technical and it's not quite in the geometric spirit as the rest of this course is. Other questions? You can find a lot about the early theory of the Bieberbach conjecture in Alfor's book. Alfor's book was written before the Bieberbach conjecture was proved. Okay, so let's plunge into this proof of the area theorem. And I'll rewrite all the notation in a moment. It's a good lesson in Stokes' theorem, which is used over and over again in complex analysis, either implicitly or explicitly. Every time you use Cauchy's integral formula in any form, or the residue theorem, you're implicitly using Stokes' theorem. It's a good exercise in Stokes' theorem to figure out how to compute the area of a region from something about its boundary. So how do you do that? Well, let's suppose first that K of F is a smoothly bounded region. So it's a Jordan domain, oriented boundary, and we want to compute the integral over K of dx dy. But we're complex analysts. So instead of working with this form, which we can think of as the exterior form dx wedge dy, what we like to work with is I over 2 dz wedge dz bar. Now this is really the same thing. Now what's the relation? You see z is x plus iy. So this is I over 2 times dx plus I dy. that's dz, wedge dx minus I dy, that's dz bar. And when you multiply things out, dx wedge dx doesn't give you anything, dy wedge dy gives you 0, but there's these cross terms. You get I dy wedge dx, so that's minus I dx wedge dy, and then here you get dx wedge minus I dy, that gives you another one, so you get minus 2i dx dy, the I over 2 cancels, and you get dx wedge dy. Okay, so to compute the area, we often use this formula, this form, which is the same as dx dy. Should have said the area of K is equal to this integral. Or sometimes it's convenient to write it this way, dz bar wedge dz. Now we want to relate this to an integral over the boundary of K. That means we want to take this differential form and write it, let me call this alpha, and we want to write it as d lambda. Because if we can do so, then we can integrate lambda over the boundary of K by Stokes' theorem and get the area of K. And a good choice for lambda here is just z bar dz. As you would expect, the d of this is dz bar dz. Okay, so this form has an obvious primitive because it's written as the wedge product of two exact forms. Okay, so the upshot is that the area of K, write it here, can be computed but as 1 over 2i times the integral over the boundary of K of z bar wedge dz. Okay, so that's the first step. Now we bring our Riemann mapping into play. We have a map from the outside of the circle, it's mapping F to the outside of K. So in particular, we can parameterize the boundary of K by the circle. And so we can do this integral by integrating over the circle. That is, we just substitute z is equal to, let me call it, actually let me call this variable w bar wedge dw, and then we substitute w equals f of z, and f of z is z plus b1 over z plus b2 over z squared, etc. And now we just compute. And so there's an important lesson here, is that when it comes to power series, you should just fearlessly compute. Power series, especially when integrated over the circle, always work out nicely. You just have to push through and see what comes out. And what should give you confidence is that when you multiply power series together, it's easy to collect terms that involve specific powers of z. And that's the main thing that we need to do here, because we're going to have to take w bar, wedge dw, replace w with f, and then collect terms and integrate. So let's do that. So then we get the area of K is 1 over 2i times the integral over the circle now of f of z bar df of z. And now, what is f of z bar? That's pretty easy. F of z bar is obtained by just barring every term in this equation. But now let's remember that if we take z bar, that's the same as 1 over z on the circle. So when we take 1 over z is really the same as z bar. So f of z bar looks like this. It's actually 1 over z because z bar is the same as 1 over z, and then the rest of the terms now involve positive powers of z. This is on the circle. On the circle, we can take advantage of this identity. Now, what about df of z? That should be pretty easy because this is just an ordinary differentiation of an analytic function, no big deal. So we just differentiate with respect to z, and we get df of z is, okay, so here we go, 1 minus, and now since this is a negative power of z, I'm going to get b1 over z squared. And then I'm going to get minus 2 b2 over z cubed minus 3 b3 over z to the 4th, and so on. So I have a 1, and then I have a bunch of minuses, and then I have a dz. Okay, now I like this a little bit better if I had a b1 over z. So what I'm going to do is I'm going to pull a z out of everything. I'm going to put a dz over z here. And now I'm going to put and compensate by writing here z minus b1 over z minus b2 over z squared with a 2 in front minus 3 b3 over z cubed, etc. Okay, and now we're ready to multiply. And when we multiply, we're going to get a sum of powers of z, and then everything is going to be times dz. And then at the end of the day, we're going to have to integrate over the circle. But let me remind you of something. What is the integral over the circle of dz over z? Who can tell me? This is the simplest instance of the residue theorem.
2 pi I.
Right, this is 2 pi I. And if you integrate z to the n dz over the circle, you just get 0 if n is not equal to 0. So what we really want to do is multiply f of z times df of z, or multiply this function times this function, and then we have this dz over z here. So all we're interested in is the constant terms. Whenever we get a power of z that's not just z to the 0, that's not a constant, that's going to integrate to 0 over the circle. So what we get is 1 over 2i times the integral over the circle of dz over z times, and now we have to see where we get constant terms. Okay, so one place we get a constant term is this 1 over z times this z. That gives us a 1. So there's a 1. Now, how else can we get a constant term? Well, if this 1 over z multiplies any of these guys, we get even more negative powers of z. So we don't get constant terms. That's the only constant term this guy contributes. What about b1 over z? Well, it's the same thing. It's only going to contribute a constant when it goes against the corresponding negative power of z. So we're going to get a, and by the way, I should have barred the coefficients here. So we're going to get a b1 times b1 bar with a minus sign. So we get minus b1 squared. And then for this term, we're going to get a b2 bar times b2 with a 2 in front and a minus sign. So we get minus b2 squared with a 2, minus 3 b3 squared, etc., which is starting to look like the area theorem. And indeed, we're almost done because this integral we already evaluated, it's 2 pi I. Here we have a 1 over 2i, which kills the 2 and the I, and we're left with pi times 1 minus the sum n bn squared. Okay, so that is the proof of the area theorem. I think it's a very slick and elegant computation, and it's based on this very useful principle that you can compute the area of a region by by integrating over its boundary. Okay, now you might critique my proof, and you should. What are some possible critiques of this proof? Well, one critique would be, I assumed the region K here was bounded. Sorry, not that it's bounded, but that it had smooth boundary. But the image of a Riemann mapping can be a region with arbitrarily bizarre boundary. Even the case z plus 1 over z, the image is a slit. It's not a smoothly bounded region. So how do you deal with the case where you have a Riemann mapping, but it's not to a region of the right type? So there's a very simple trick to handle the general case, which is what we do is instead of considering our function f, which is defined on the outside of the disk, we consider the function f of z divided by r. I'm sorry, yeah, that's right. Let me write it this way. F of r times z, where r is a little bit bigger than 1. So when you plug in a point on the disk, you actually first multiply it, move it from the circle to r times z, and then you apply your mapping f to it. And remember that no matter how bizarre this region K is, the image of the disk of radius r bigger than 1 is some beautiful real analytic curve that approximates this possibly fractal region K. And so we can apply the argument, provided instead of looking at the outside of the circle of radius 1, we look at the outside of the circle of radius capital R. And so we apply the argument instead to this function, and then we take a limit. And because the area of the K for radius R converges to the area of the K for radius 1, as R goes to 1, the same conclusion holds. Okay, that's a very typical method in conformal mapping. We can often reduce to the case where the boundary of the region is smooth or even a real analytic curve. Okay, so that's the proof of the area theorem. So let me just write that down again. We have, in particular, 1 is greater than or equal to the sum of n bn squared. And in particular, the absolute value of b1 is less than or equal to 1. Okay, so now let's turn to the proof of this theorem for f and s, which is that the absolute value of a2 is less than or equal to 2. Now, there's a very tempting idea, which is since things work so well in sigma, let's just take functions in S and turn them into functions in sigma. So given f and s, let's look at this new function, f of z. Now, the functions in sigma send infinity to infinity. The functions in S send 0 to 0. So how can we get a function that sends infinity to infinity and is defined on the outside of the disk instead of the inside? Well, we just take 1 over f of 1 over z. So this function, capital F, now sends infinity to infinity. It's still 1 to 1 on the Riemann sphere because all we did was compose with Mobius transformations. Is it in our class sigma? Well, almost. Let's again be brave and see what its power series is. So the power series for this is what? This is 1 over, and then we know the power series for f. So f is the sum of a and z n. So f of 1 over z starts like this. It's 1 over z plus a2 over z squared plus a3 over z cubed, and so on. And we want to make this look like the functions in sigma. It should have a Laurent series about infinity. So how can we do that? Well, let's multiply the top and the bottom by z. So we get we get z over 1 plus a2 over z plus a3 over z squared, and so on. And now remember, we're interested in z being large. So we have 1 over 1 plus something, and this thing is small when z is large. So now we use, again, our favorite power series. 1 over 1 plus w is 1 minus w plus w squared minus w cubed, and so on. And what we find is capital F of z is z times. So we get 1, and then we have to subtract off this term. So minus a2 over z plus a3 over z squared, etc. And then plus a2 over z plus a3 over z squared, etc. squared, minus, etc. And if we collect terms, we get z times 1 minus, and then here, this is the only term involving 1 over z. But for z squared, we get this term, minus a3 over z squared. And then we also get the first term when we square out this expression. The square of its leading term is going to be a squared over z squared. So plus a squared over z squared, and so on. So the power series begins z minus a2 plus, this was a2 squared minus a3 over z plus something over z squared, etc. Okay, so is this function in our class sigma? Unfortunately not. In our class sigma, we normalized so that the function begins with z, and then there's no constant term. And then we have powers of z, z squared, and so on. So we were able to normalize a little bit better in sigma than we were in S. And when we try to go as simply as possible from one place to the other, there's unfortunately this term minus a2 that appears. Okay, well, in any case, let's just add that in. So if we take a2 plus 1 over f of 1 over z, this function is in sigma. And that'll get rid of this term. And now we can use this fact that b1 is less than 1. Okay, so what do we get? Well, we get this strange, combination of a2 and a3. So what we get is that a2 squared minus a3 is less than or equal to 1. And this just shows you the kind of rabbit hole you go down when you start studying the coefficients of Riemann mappings. They satisfy millions of relations and inequalities. All these relations have to hold by compactness. But this is not the one we wanted. We wanted something very simple. We wanted to bound on a2. And unfortunately, we got something that mixes a2 and a3. Well, at least that's progress. So now there's a very cool trick which finishes the proof. And this will be the last thing I do with power series, but I think it's good to see a little bit of this kind of calculation. Our next trick is to notice that if f is an S, then the square root of f of z squared is also an S. Now you might think, what does that mean anyway? How do you know which branch of the square root to take? Well, let's think about what this expression means. Let's write it out formally. So the square root of f of z squared is the square root of, and then we have z squared plus a2 z to the 4th plus a3 z to the 6th, and so on. And then we can factor out the square root of z squared and call that just z. So we get z times 1 plus a2 z squared plus a3 z to the 4th, and so on, all to the 1/2. And now we're taking the square root of a function which is equal to 1 when z is equal to 0. Well, there's a well-defined branch of the square root. As long as these other z's are small enough, it's the branch that, that gives the square root of 1 equal to 1. And so we can now use the fact that, at least for w small, 1 plus w to the 1/2 is 1 plus, by the binomial theorem, 1/2 w plus 1/2 times minus 1/2 over 2 w squared plus, etc. We'll only really need this first term here. So this is equal to z times 1 plus 1/2 a2z squared plus higher order terms. And multiplying through, this is z plus 1/2 a2 z cubed plus terms of size z to the 4th. So we did this beautiful thing. We started with a function in S and we got a new function in S where a2 is now 0. There's no coefficient for z squared, and the new a3 is 1/2 of the old a2. So this is the new a3. For any f in S, we can make a new f whose a3 value is 1/2 of the old a2. And if we now apply this inequality to the new f, what we get is that, well, a2 is 0, so we get that the absolute value of 0 squared minus a3 is equal to 1, which is minus 1/2 minus, let's see here. I made a mistake with my a2. Let me see here. Let me just check my notes. Oh no, of course, this is fine. So minus 1/2 a2 is less than or equal to 1, and so this implies a2 is less than or equal to 2. Okay. So that was a little dive into the theory of coefficients of univalent functions. Now, how do you use these kinds of results to prove more geometric theorems like the Kubo 1/4 theorem? In fact, the Kubo 1/4 theorem is equivalent to this theorem, this found on A2. So the statement that a normalized Riemann mapping, its image contains a disk of radius 1/4, follows from this coefficient bound. That's one of the reasons this coefficient bound is so important. So keeping that in mind now, can add that to things we know. That A2 is less than or equal to 2. We can now prove that for f and s, the distance from 0 to the boundary of the image is always greater than or equal to 1/4. Okay, so the proof of this, what we do is we say, well, here's our image U. 0's in the image, it's the image of the unit disk. And now there's some point P, which is not in the image. So it's not in U. And we want to know how small P can be. So what we notice is that if P is not in U, then we can apply a Mobius transformation to move P to infinity. So we can just compose with the Mobius transformation A that sends 0 to 0, but it sends P off to infinity. And it should have a derivative of 1 at the origin. So what's a Mobius transformation like that? Well, you can take A of Z is Z over 1 minus Z over P. And the assertion is if F is an S, then A composed with F is also an S. Okay, so let's do one last dive into power series and figure out what A composed with F looks like. So A composed with F of Z is F over 1 minus F over P. So F is Z plus A2Z squared plus etc. And then 1 over 1 minus F over P is 1 plus F over P, which is Z plus A2 Z squared, etc. over P, plus the same thing squared, and so on. And so if we start working out the power series here, we take Z times 1 and we get Z. That's good. So this function is still normalized the way it needs to be to belong to S. And then what's the coefficient of Z squared? Well, there's one coefficient of Z squared coming from this term, A2 times Z squared, but we also get a coefficient coming from this term, Z and Z over P. So we get another term here, which is Z squared over P. So 1 over P, Z squared. And then we get terms on the order of Z cubed. Okay, now what we do is we say, well, we already know that A2 is less than or equal to 2. And here is our new A2. It's the old A2 plus 1 over P. So we can conclude that A2 plus 1 over P is less than or equal to 2. That already shows that P can't get too close to 0. And what's the exact bound? Well, this is greater than or equal to the absolute value of A2 minus 1 over the absolute value of P. And the absolute value of A2 is at most 2. Sorry, I'm writing this wrong. It's greater than or equal to 1 over the absolute value of P minus the absolute value of A2, which is greater than or equal to 1 over the absolute value of P minus 2. And so 4 is greater than or equal to 1 over the absolute value of P, and so the absolute value of P is less than or equal to 1/4. And that's the couple 1/4 theorem. Okay. Now there's a multitude of similar theorems about.
Oh, so you typoed the inequality at the end.
Sorry?
It's absolute value of P greater or equal to 1/4.
I typoed which inequality?
The last one.
Thank you. Good. Okay, so now I want to conclude by just mentioning the way you should think about univalent functions and all of these inequalities. It's nice to be able to take a deep dive and get specific estimates, especially when the constants come out so simple, like 1/4. On the other hand, what's really useful to know are these compactness theorems. And so, for example, there are theorems of the following type. You say, suppose F is an S, and then almost anything you can think of, there's a theorem about it. But the shape of the theorem is usually the important thing, not so much the exact bounds. So if F is an S, for example, then the absolute value of F of Z is less than or equal to some function that depends only on the radius R for all R strictly less than 1 and for all F and S. So in other words, the image of the ball of radius R can't get too big under a Riemann mapping, even though the image itself might be an unbounded domain. We might have a Riemann mapping that goes to an unbounded region, but the image of the ball of radius R strictly less than 1 has universally bounded diameter. But in fact, you could also add to this not just that f of z is bounded, but f prime of z is bounded, and f double prime of z are bounded. Any finite number of derivatives you want to control are controlled by some constant over the ball of radius r, just because the space of all Riemann mappings is compact. So for example, the curvature of the boundary of this region, the image of the ball of radius r, is controlled. So I should have drawn the ball of radius r in yellow. Here and here, and then the rest of the disk in white. And remember, the boundary of view can have all sorts of terrible fractal stuff going on, non-local connectivity. It's just bizarre. And yet, the image of the ball of radius r, where r is fixed and strictly less than 1, is a bounded distortion region, a bounded eccentricity, bounded curvature, and at the edge is a real analytic curve. It's as nice as possible. Okay, so the reason I draw the picture this way is the way I think of it is when you take an egg and you apply the Riemann mapping to it, the white of the egg can splatter. It can go all over the place. It can even stream out to infinity. It can have all of these fractal cracks in it, but the yolk of the egg always remains good. It always has bounded geometry. And that's really the upshot of all of these distortion theorems. Okay. So there's one last example in conformal mapping that I feel I would be really remiss if I didn't talk about it, and that's the triply punctured sphere. So we've talked about simply connected regions. They're almost always isomorphic to the disk. We talked a little bit about doubly connected regions, like the annulus, like the punctured disk, but we didn't talk about triply connected regions very much, or arbitrary domains in the Riemann sphere. But in fact, it's a theorem which we haven't proved yet, and we could, but in the interest of time, I won't, that the universal cover of any region in the Riemann sphere, unless its complement consists of just 1 point or 2 points, is the isomorphic to the unit disk. So let me just write that as a theorem. If U is contained in the Riemann sphere and the cardinality of the Riemann sphere minus U is greater than or equal to 3, this implies the universal cover of U is isomorphic to the unit disk, or upper half plane if you prefer. And therefore, any region with 3 or more points in its complement has a hyperbolic metric on it, and it has a kind of Riemann mapping. The Riemann mapping is no longer an isomorphism, it's a covering map from the disk or the upper half plane to our region U. And the most extreme example is when you just take away 3 points from the sphere. So this theorem I will discuss, which is that there exists a universal covering map, lambda, from the upper half plane, pardon me, to the Riemann sphere with 0, 1, and infinity removed, or if you like, the complex plane with 0 and 1 removed, such that lambda is analytic. And once we have this, we then get, if we call this region U, this complement here U, we then get a hyperbolic metric on U and all sorts of interesting hyperbolic geometry of the triply punctured sphere. Now, one of the reasons this theorem is important is it implies a lot of very strong rigidity theorems, one of which is called the Little Picard Theorem. So So the little Picard theorem is a great strengthening of the statement that a bounded entire function is a constant. It says it's not necessary that the function is bounded. All that's necessary is that it omits two values in the complex plane. So let me be concrete about this. Let f from the complex plane to itself be an entire function. This just means an analytic function on the whole complex plane, no poles. Suppose there exist 2 points A and B and C such that the image of f does not contain A or B. And it does not contain B, doesn't contain A or B. Then f is constant. So for example, you might ask, if I have an entire function, does it have to have zeros? The answer is no. There are entire functions that have no zeros. Polynomials always have zeros, but there are more exotic functions that have no zeros at all. Who can give me an example of an interesting entire function that has no zeros?
E to the z.
E to the z, thank you. So an example is e to the z maps the complex plane to the complex plane with the origin removed. It has one omitted value. In fact, it turns out to be a covering map. But we don't need that for the moment. But you might ask, well, is it also possible that e to the z has another omitted value? For example, what if you take the number 1? Is there anything that maps to the number 1? Well, in fact, there's a whole bunch of things that map to the number 1. 0, 2 pi I, and in fact, any z in that's an integral multiple of 2 pi I. So there's big fibers over all the other points, even though the origin is omitted. And this theorem says you can, for an arbitrary entire function, you cannot omit two values. So maybe it never assumes the value 0, but then it has to assume the value 1 and indeed every other value in the complex plane. And as we can see, that's sharp because of e to the z. Okay, now the proof of this is almost alarmingly simple. So here's the proof. Well, first, if you have a function that omits two values, we can translate. So one of the values is 0, and then dilate, so one of the values is 1. So we just have to understand entire functions that omit the values 0 and 1. So if f omits the values 0 and 1, it gives a map from the complex plane into this domain I was calling U. And the universal cover of U is isomorphic to the upper half plane. And we have an analytic function lambda, which is a covering map. Well, by the theory of covering spaces, there exists a lift of f to a map to the upper half plane. And in fact, the upper half plane is isomorphic to the unit disk. So we could compose this lift with this isomorphism, and we would get a bounded entire function on the whole complex plane. Well, that's obviously constant. But since this function is constant, this function also has to be constant, and that's the end of the proof. Now, interestingly, this proof was considered very subtle and almost suspect by early complex analysts because of the fact that it used the theory of covering spaces, which came from a different mathematical domain. But I think today we think of this as the obvious and efficient proof of this kind of theorem. Now, since I've mentioned little, I should also say what the Big Picard Theorem says. It says that you can jazz this up a bit and say that if f is not an entire function, but it's just a function with an essential singularity, so it has an isolated singularity, say at the origin. For example, it might be the function e to the 1 over z. If you have an isolated singularity of an analytic function, then in any neighborhood of that singularity, the function omits at most one value. So let me just write that down. Big Picard, an analytic function omits at most one value near any isolated essential singularity. And a typical example of this is e to the 1 over z, which has an essential singularity at z is equal to 0. It's not too hard to soup up this theorem and use the Schwarz lemma to prove the Big Picard theorem, but I won't bother doing that. Okay, so what I want to explain is this theorem, that the triply punctured sphere, the universal cover of the triply punctured sphere is the upper half plane. And so it has a hyperbolic metric on it. And then it should kind of come as no surprise that once this is hyperbolic, any open domain inside of this is even more hyperbolic. And that's what this theorem asserts. Okay, so there's two proofs. So let me ask, just as general my own education, let me ask people to raise their hands if they studied the theory of elliptic functions. Raise their virtual hands. Go to reactions and click raise hand. Okay, so we have, it's not enough to convict Trump, but we have something close to a 50%. So I'll go through this. I don't want to give a whole course on elliptic functions, but I'll try to explain as I go the first proof, which involves elliptic functions, and the second, then there's another proof which involves hyperbolic geometry. And you may want to review the section on elliptic functions in Alfor's book on basic complex analysis if you don't have this background already. So the proof is based on a beautiful idea. There's actually a very natural way to take a point in the upper half plane and get a point in the triply punctured sphere. And here's how it works. We start with tau in the upper half plane. From tau, we get a lattice. Lambda z plus tau z. So the picture of this is, here's the origin at 1, and then here's your point tau, and these two vectors generate a subgroup of the complex plane. It has minus tau in it, and so on, minus 1, etc. They give an action, in fact, of Z2 on the complex plane by translation, and a fundamental domain for that action is this parallelogram that I've drawn. And what the group does is it glues this edge to this edge of the parallelogram, that's translation by 1, and then this edge to this edge, that's translation by tau. So when you take the quotient of the complex plane as an additive group by lambda, what you get is the first interesting example of a compact Riemann surface after the Riemann sphere. It's an elliptic curve. It's topologically a surface of genus 1. And its fundamental group is isomorphic to z squared. And in fact, this is its fundamental group, and its universal cover is C. This is just the presentation of E as the quotient of its universal cover by a group of deck transformations. Okay, now, there's a beautiful idea here, which is on E, you can find a map to the Riemann sphere. And this map is 2 to 1. And it's the simplest thing you can think of that would be 2 to 1. It's what you would call an even map. which means that in the group law on E, it satisfies P of Z is P of minus Z. So if you like, it just glues each point to its inverse in this torus E. So in other words, it gives you the quotient of the torus by the involution, Z goes to minus Z. But the map, Z goes to minus Z, has a fair number of fixed points on E. In fact, it has 4 fixed points, namely the points of order 2 in the group law on E. So E itself is isomorphic as a group to S1 cross S1, and its points of order 2 are isomorphic to the points of order 2 on the circle, which is a Z mod 2, cross another Z mod 2. Geometrically, if I blow up the fundamental domain, so this is 0, tau, and 1, the points of order 2 correspond to the origin in the group, and then tau over 2, 1/2, whose double is 1, which is in the lattice lambda, and then this midpoint here, which is 1 plus tau over 2. And those correspond to the 4 points I've drawn in this picture of E. They're the fixed points of Z goes to minus 1 over Z. So when you map the torus to the Riemann sphere by this analytic map, there are 4 natural points in the image. Namely, the images of these points of order 2. And in fact, one of them is kind of canonical. It's the image of 0. And then if I know what tau is, I could call this point E1, E2, and E3. And then I could look down here at P of E1, P of E2, P of E3. Now the thing is, the map to the Riemann sphere is not quite canonical. You could always compose with a Mobius transformation in the target. Well, let's use that to our advantage. We could normalize that in the coordinate Z on the Riemann sphere, the origin in the torus maps to, say, the point at infinity. And then the point E1 maps to 0, the point E2 maps to 1, and the last point maps to some number, which we're going to call lambda. So in other words, lambda is the cross ratio of the images of the 4 points of order 2 on the torus. And this function P, by the way, is up to a normalization. It's the famous Weierstrass P function. There's an essentially unique such function up to composition with no Mobius transformation, and there's explicit formulas for writing it down. Now, what happens when you change the value of tau? What happens is everything moves here. The fundamental domain changes, this function changes, and this cross ratio changes, but it turns out to change analytically. And in fact, this covering map is defined by the procedure I just told you. So lambda assigns to tau the cross ratio of the image of the points of order 2 on the corresponding elliptic curve under the Weierstrass P function. And now you need to do some work to prove that this is actually a covering map. But that's the idea of the construction. Now, a very natural question would be, if that's a covering map, what is its group of deck transformations? What are the automorphisms of the upper half plane such that lambda composed with A is equal to lambda? That's the definition of the deck transformations for a covering map. And it turns out that the group of deck transformations, the deck group, is equal to what's called gamma of 2. It's a subgroup of the group of matrices with integer entries and determined at 1. So it's the set of A and SL2Z such that A is congruent to the identity mod 2. In other words, the on-diagonal elements are odd and the off-diagonal elements are even. So in other words, it's A, B, C, D equal to 1, 0, 0, 1 mod 2. And these transformations act on the upper half plane by z, or I should say tau, goes to a tau plus b over c tau plus b. Okay, so that's sort of the highbrow, if you're well versed in elliptic functions, the highbrow way to see that this universal covering exists. Let me tell you, just to conclude today, a much more geometric way to prove this, which is quite cool. And what you do, this is proof 2. What you do is you draw in the upper half plane what's called an ideal triangle. So you draw 3 hyperbolic geodesics. They all are making 90 degrees with respect to the real axis. Say the endpoints are 0, 1, and infinity. And now you apply, you use the Riemann mapping theorem. So call this region U. There's a Riemann map that sends U isomorphically to the upper half plane. And it sends, you can arrange that it sends 0 to 0 and 1 to 1. So this region here and infinity to infinity. So this ideal triangle gets sent to the upper half plane by basically squishing this arc down and moving these 2 arcs so they map to these 2 pieces here. Anyway, the existence of such an F is guaranteed by the Riemann mapping theorem, and of course it extends continuously to the boundary because this is a Jordan domain. But now we can apply Schwartz reflection through this arc here. So if we take this triangle and reflect it through this arc, we'll get another triangle down here. And if we take the upper half plane and reflect through this arc, we get the lower half plane, minus h. So you can extend F by Schwartz reflection to a map that sends this region here to the lower half plane. And then you can extend it by reflection through this side to a map that sends this tile also to the lower half plane. And then this tile also to the lower half plane. But then it sends this tile over here back to the upper half plane. And now you keep reflecting through the sides of this ideal triangle over and over again. And eventually you get a familiar tiling of the upper half plane. And that extends this to a map of the entire upper half plane to the union of the upper and lower half planes, but we never hit the points 0 and 1. And since the original map was a Riemann map, it was a homeomorphism, the whole thing is a covering map. And that presents the upper half plane as the universal cover of the triply punctured sphere. Okay, so I think I'll stop with conformal mappings there. And please take a look at especially the course notes on harmonic functions, because we're going to plunge into that topic when we return next week. Okay.
Thank you.